Welcome to the October 2022 Engineering Series, guest speaker of NORAD. I'm Silvio Baldessera, chair of NORR, founder of NORAD, and host. NORAD is a continuing education program founded 15 years ago, and the three main goals are to teach, learn, improve, and to do that continuously. The program relies on bringing the best guest speakers in three series: architecture and engineering, which are of equal importance, and masters, where we learn from the past. Each of the NORAD sessions, starting in 2020, have been recorded with the guest speaker's permission and are available on NORAD YouTube for global access. Today's session will be posted in 1 week. Welcome to our NORR 14 office staff and our invited guests globally. Welcome to the invited students from the 14 schools of architecture in the USA, Canada, and the UK. You will be the future of architecture and engineering. In 1936, architects Louis Skidmore and Nathaniel Owings started their firm in Chicago, and in 1939, engineer John Merrill joined, forming SOM, which today is one of the world's leading architecture, urban design, and engineering firms. Leading engineers at SOM have included John Merrill, Fazar Khan, best known for the Wills Tower and John Hancock Tower, and then Bill Baker for the Burj Khalifa in 2010. In 2018, Bill Baker and SOM, in collaboration with MAMA Contemporary in Chicago, mounted an engineering exhibit of SOM buildings showcasing models stripped away the building architecture skin. Bill Baker opened the show with a quote: "An engineer should design a structure that an architect would be ashamed to cover." Bill Baker is one of the world's leading structural engineers. He has designed innovative structures that range in scale from single-family homes and small pedestrian bridges to the world's tallest man-made structure, the Burj Khalifa in Dubai. His cutting-edge designs include unique Broadgate Exchange House in London, which is both a building and a bridge and spans over Liverpool Street Station, and the cable-supported entry pavilion for the General Motors headquarters in Detroit. Additionally, Bill is widely recognized for his collaborations with renowned artists. Many of Bill's structural innovations are a result of his extensive research into structural systems, which he shares through his teachings, lectures, and numerous publications. He is an honorary professor at the University of Cambridge and is also taught at MIT, the University of Illinois, at Urbana-Champaign, Illinois Institute of Technology, Northwestern University, and Princeton University. Bill has received honorary doctorates from University of Stuttgart, Heriot-Watt University, the Illinois Institute of Technology, and the University of Missouri. He has been honored with the gold medal from the Institution of Structural Engineers, the American Society of Civil Engineers, Lifetime Award for Design, the Gustav Mangel Gold Medal from the University of Ghent, the Fazar Raham Khan Medal from the Council on Tall Buildings and Urban Habitat, and the Fritz Langhoff Prize. I present to you Bill Baker, who is share with his presentation on philosophy of design. Bill Baker.
Thank you for that for that introduction, and I'm pleased to be here today, and thank you for asking me to do this. So today I'm going to talk about a philosophy of design. And I think this is an important topic which needs to be, part of the education of young architects and engineers. And I think it affects the way that we look at projects. And I'd like to start with just kind of setting the frame with, you might say that architecture is a story of a time and place. Here we have a picture of a King's College Chapel. It was finished 500 years ago, started about 575 years ago. And, it speaks to its time and the culture in which it was created. But you might say that this story, in the story, structure forms the words of that story. Here, you see the flying buttresses, which create the armature on which the thrust of the building is resisted, or in the incredible fan vaults above your head when you're in the chapel, that these structural elements are the architecture. The architecture is the structure, and they're inseparable. And this amazing roof, which is held together by geometry and gravity, there's no reinforcing. It's held together by a proper understanding of engineering principles that made this incredible structure possible. And those are the words that enabled the creation of the story of the architecture. There were some additions to the language in the last century or so, which are really quite remarkable. You look at the work of Robert Maillard with his incredible arches, which he designed while he was designing the forces. He designed the geometry of the structure and the geometry of the forces at the same time. And you can imagine the feedback loop he got in that process. Or the work of Felix Candela, which is these incredible hyperbolic paraboloid shells with amazingly thin edge that has been there for quite a while, since 1958. Or of course the work of Beneš and Friado in this tour de force, which is 50 years old this year, of the Munich Olympic, or some other work by Friado of the incredible timber grid shell at the Mannheim Multihalle, which created new possibilities in architecture through expanding the language that's available through the language of structure. Now, in recent times, I have to say there's been some additions, but I'm not quite sure how to describe them. Is it about a purity of structure, or just what is it we can do? And here are buildings that were proposed, several years ago, including some by SOM, another set of, proposals, including one by SOM. And when I go overseas and I go to these cities like to Shanghai or the Middle East and the like, and I look at these buildings that are out there, in Shanghai, you might say you have the SOM pagoda next to the KPF bottle opener, with something that's supposed to be a dragon in the back with a shish kebab out front. And this makes me think about the movie Brazil, and I urge all the young architects on the call to watch the movie Brazil. It has a lot of architectural overtones. Anyway, those buildings remind me of this particular character, Ida Lowry, and particularly her hat, where so she has something interesting. She absolutely stands out because of her hat, and so if you saw this woman walking down the street, she would stand out, but then maybe not. And when I look at all these buildings with these kind of look at me tops to them, they remind me of having dinner in a crowded restaurant where everyone's shouting and you can hear no one, and everyone drowns out each other trying to be get their point across, or as these people here trying to stand out in the crowd, and in a sense no one stands out. So with that kind of as a background is where we are. We certainly at a very special point in time, we design a world where we have a climate crisis. There's an existential issue out there that we need to deal with. But we also in a world that has to grow. We have a lot of great demands on housing and places to work, so that we have a world that needs to grow. We have limited financial resources, but we need to expand. We hope we can have prosperity for people also. Now, one of the things that we often do see is we see a world of I would borrowing a phrase from an economist, a world of irresponsible excess. But having said that, we also need to have dreams and inspirations, and everything can't just be the hair shirt minimalist solution. There's got to be some things that are inspiring, such as one could say, to us as designers, are we facilitators of dreams and creating wonderful new things, but are we also sometimes enablers of willful excess? And we need to have that discussion. And to my mind, it's not a very black and white discussion. It's a full of gray, because one could say this is a very expensive way to make a restaurant. Of course, the world without the Eiffel Tower, without the dreams and aspirations that it embodies, would be a lesser place. One cannot imagine Paris or Europe or the world without the Eiffel Tower. But there are also buildings that have been out there that have been built that I might say are icons of willful excess. And so for that, let me leave it to your imagination. I'm sure you can all think of a project that you look at and say, really? That we needed to do that. We needed to spend all those resources to create that particular building. And so based on that, as designers, we have a responsibility. We have a responsibility to have a position, okay, to know what it is we're doing, why we're doing it. And just following orders is not an answer. Because a client wants something, do we provide it? Which is a very, very difficult conversation to have internally or externally. Just because we can do things doesn't mean we should. I mean, the things I as an engineer can engineer today are like incredible. Not necessarily doesn't mean they're a good idea or they need to be built, but I can certainly figure out a way to do it. And so my suggestion is there needs to be a critical discussion, where we discuss these things, particularly in the light of the world that we live in today. And I think a starting place is for designers to have a personal philosophy in design. And in my own search for this, a very critical thing was when I was working on a project with this artist, James Turrell. James Turrell is a famous artist. He's done this art installation in this extinct volcano behind him in Arizona, which is called Rodin Crater. And so we were working with James on an extension, an additional installation to be put on in Rodin Crater. And here you see a 3D view of Rodin Crater, and here's the main crater. And here is this side vent that's called a fumarole, which is a side vent of a volcano. And we're looking to do an art installation in this fumarole. And the nature of the design, we have this, and the purpose of this is to essentially be a lunar observatory to watch moon rises and moon sets for the next 2,000 years. It has a dome over the top of it, and in section it has this 40-foot diameter, 12-meter sphere where the light from the moon rises comes and projects against the back surfaces. So there's a lens in the front, and when we got involved, James had the ideas together, but it was a bit of a train wreck. Things were kind of crashing. There's a lot of ideas, a lot of things there that were kind of like getting jumbled together. And so what we focused on was giving it a hierarchy where, when things had a conflict, the sphere was alpha. It was number one. It got the right of way, followed by there was a cylinder around the outside. That was number two. And in the process, we made it organized. And then James and I were making a presentation to a potential donor, And I described what SYM brought to the table was Miesian simplicity. Now, I said that because I grew up in an office. A lot of people came into Mies van der Rohe's office. Some of my mentors were important players in Mies van der Rohe's office. And so he, so I said that, we gave this Miesian order, and James corrected me. He said, no, Quaker simplicity. Now, I was raised Calvinist. I had no idea what that meant, what Quaker simplicity meant. So I was really intrigued by those 4 words, and I started going to Quaker services to try to understand it and research what did he mean by those words. And since I'm not Quaker, I can make a very gross generalization of some of their Quaker values. But can you imagine that if you were a young boy and you're raised to believe in simplicity in speech, clothing, food, and your mother always said to you, step into the light. And then later you became an artist. Maybe you're no longer religious, but you were raised with this ethical situation and you became an artist. What might you create? Here is one of James's creations. What you see here floating before you is a pyramid of light. And it is so simple that it doesn't even exist. This pyramid is created by your eye. What it really is, you have light behind the wall that's illuminated. You see in the corner of the room, and it is your eye itself that creates the pyramid. So I look at this artwork and I see it is the manifestation of these values in which he was raised, of simplicity and stepping into the light. And that made me start to think about what is it that I value, or what is my ethical position, not unrelated to aesthetics, and how does that affect my aesthetic position? So I started to examine the things that I value. Here's another project we did with James down at Rice University a few years ago. Once again, simplicity and light. So I proposed for myself a set of values that I think that were the things that I value and how they relate to art and architecture and engineering. As an engineer, I believe in efficiency. It's great. It's terribly rewarding. It's kind of what we're trained to do as engineers, to do something efficiently, like such as this entrance to the General Motors headquarters in Detroit, this cable structure that we engineered several years ago. Is about the efficient delivery of forces to the structure, or simplicity, such as this band shell we did with Jamie Carpenter, or minimalist. I like minimalism, such as Mies's Farnsworth House near here in Plano, Illinois, or economy. This is the Exchange House project in London that was mentioned earlier, where this is amazingly, for what it's doing, it's an amazingly efficient structure. It spans 78 meters over the trains coming in and out of Liverpool Street Station. And without an efficient structure, it would still probably be open to the sky and a kind of a wound in the middle of the city of London. I believe in elegance. As you go across the prairies here in the Midwest or in Western Canada, and you see these incredibly elegant irrigation systems, totally functional, but totally elegant. I believe in utility. You go back to Vitruvius, his 3 values of utilitas, firmitas, venutas, utility, firmness, and commodity, and delight. I believe in that, things should have a harmony, a rhythm to it. I believe in hierarchy and order, but in the sense, not in the hierarchy of ideas. I don't care who the ideas come from a summer intern or from a partner, doesn't matter. But I do believe that there's a hierarchy and order to how we tell the stories of our buildings, and not everything is equal. And I'll speak to this a little bit more later. I like clarity. I like where you can see what is happening and how the loads for this residential project I worked with Jeannie Gang on, where we're trying to take, the seismic, this is in California, trying to take the seismic loads from this sleeping unit above down to the living unit below. Proportions, very, very important. This is a house I did with Thomas Pfeiffer in New York. Appropriateness. Now it's hard to come up with, to say what's appropriate. So I found a photograph of something which is, for me, totally inappropriate. I hate when people use structure as decoration and not the real thing. Whoever house this, they definitely want it to have a colonnade up front. So that here you have it. Makes no sense structurally. I think it should be appropriate and try to avoid inappropriateness. And for the life of me, I can't figure out how that garage works either. I do like rational designs where it's very clear and organized, such as the John Hancock building here in Chicago. And one of the things that I think is important in my position is that if you want your design to actually get built, you should have at least one idea of how to build it. And I think this is a very, very important part of the design process is considering how it's going to be built as part and make that integral to your design. That was true of Exchange House, or this is the construction site of Burj Khalifa. We had form work on this project that was used 160 times, and that was central to the original design. And for the young architects and engineers on the call, don't be afraid to re-examine past systems and solutions. Seems like every time I work with a young designer, what they would like to do is they would like to do something that's never been done before. Well, don't constrain yourself that way, because one could say the chair problem has been solved. There's no need to ever design another chair. Well, Corbu had another idea, and so there's some other ideas, and there's some other ideas within a fairly narrow design problem. Okay, some places you sit, sometimes you got a back support, sometimes you don't, but a very narrow design problem. In fact, right now I'm trying to work on the design of a chair. It's quite a wonderful exercise to go and replow the field that's been plowed by so many other people in the past. Another thing I find very, very helpful is what I call describe your design in words. And but you don't want to do this too early. And one of the things I do when I'm working on a project, when I think we've got it kind of figured out, when it's starting to come together and the ideas are starting to gel, I try to describe it in words. And if it takes too many words, maybe I'm not there yet. And occasionally you can get really lucky where you're quite concise. Sometimes and this has been this whole issue about getting to something concise is a lot of work. It happens in architecture, as we edit our designs and refine. As we all know, making something simple is not very easy. It takes a lot of work. And this applies to others, like Mark Twain has this famous quote, I didn't have time to write a short letter, so I wrote a long one instead. And I think almost every culture has a similar quote from someone. I also like this particular quote from Winston Churchill. I'm going to make a long speech because I have not had the time to prepare a short one. But sometimes if you work very hard and you have the time and you're able to get it refined, sometimes you can get down to a very short, concise thing. And sometimes you can get it down to even a noun plus an adjective. For example, the John Hancock is a braced tube. Each word is very important. Obviously it's braced, but also it's a tube. It's not a truss. It's in the classic sense of where all the load goes into the cords. It's a tube. where the loads are distributed to all the columns on the face. So it acts like a tube, or a bundled tube, the description that was used to describe the structural system of the Sears Tower, now called the Willis Tower, or the buttress core that we used for the Burj Khalifa. Now, once you can describe the essence of your design in a few words, now you can't always get to 2 words, sometimes it'll be a short phrase, but once you do that, the advantages are you clarified in your own mind what it is that you've created and what it is you're doing. You can help it, you can explain it to the rest of your team so that you're all moving in the same direction. You can explain it to the other disciplines so they understand the essence of what you're doing. You can explain it to the contractor and to the owner, and it helps you resolve conflicts, because tall buildings or architectures all about conflicts, where you have multiple demands looking to use the same space usually. And how do you resolve this? Well, it helps to understand what is the most important thing that should get the right of way when these things come together. It's also important for a firm to have a philosophy. As we said earlier, SOM has been around since 1936, and so that's multiple generations of partners. And so so a few years ago, we were doing some pretty good architecture, but there was 1 or 2 buildings which were really good, but maybe SOM should not have done them. Okay, and so all the partners got together, all the design partners, that is. So, there was the architectural design partner. I was there as a structural engineering design partner, interior design partner, urban planning design partner. And we met in Philip Johnson's glass house in Connecticut and talked about what was the essence of SOM, what was important. And we came down to 3 terms: simplicity, structural clarity, and sustainability. And so that we tried to have that as a guidepost to lead us forward as a design practice. Now, this list is not written in stone by Moses or given to Moses, written in stone, but it is a point for us to have discussions about how we interpret this and how we evolve this as time goes on. And so a few years ago, I was asked by Detail to do a book on SOM structural engineering. And so I use that as an opportunity to take some of the things I've just presented to you and kind of organize it into this book. And we decided to make the book about ideas and not necessarily about projects. Now, projects might help explain an idea, but it wasn't necessarily it wasn't focused on projects, but it was focused on ideas. And so I'm going to go through some of those and try to expand on kind of the thoughts and the philosophy behind some of this as we go on. First of all, simplicity plus clarity. I think that's very important part of the legacy. You look on the left, that's Kitt Peak Observatory led by Myron Goldsmith, an interesting architect engineer. He actually joined SOM. Well, first of all, he studied under Mies van der Rohe, and then he studied under one of the world's most famous architects. And then he studied under Pier Luigi Nervi, one of the most famous engineers of his era. He then joined SOM as a structural engineer in San Francisco, as a head structural engineer in San Francisco. He then switched to architectural design and eventually became an architectural design partner here in Chicago. And so this is one of his early projects, the solar telescope, and it's like just the essence of simplicity. Or another project on the right, the world's first tubular building, which the Chestnut DeWitt building here in Chicago, which is the world's first framed tube. Or the simplicity and clarity of this art piece we did with James Terrell, or the Jamie Carpenter band shell, or this Tower of Hope that we did with Jabin. A very, 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 very important topic, which I don't think it is addressed nearly enough, is the issues of scale and form. Okay, and let's start with issues of scale. On the left is a drawing that was actually made by Galileo, I think in 1638 or thereabouts. And so, you look at this, is that right? Well, it turns out, depending on your assumptions, it is right. If you had a bone that, say, it was a cantilever, say, if you look at the camera, and say I have this thing cantilevering out of my hand, and let's say it's right at the breaking stress, and the total, and it's solid, and let's say for the moment it's round, and that and so the weight on it is itself weight. So if I decide to make it 3 times longer, as in this drawing here, that means it has to get bigger. But as I make it bigger, it becomes heavier. So under those set of rules, if I make it 3 times longer, it has to be 9 times wider. And that's what Galileo has done here in his drawing experiment. And of course, the very, very famous book by Darcy Thompson on growth and form. I've got, I think, probably 3 copies. One in my office at the downtown, and a couple, one in my home office, and another down in the living room of my house. Of course, Darcy Thompson was a biologist. You might say he was a biologist who knew quite about instrument mechanics. And why do things in nature look like they do? And mostly it's about a reaction to the physics of their environment, not unlike how it should be for architecture. And certainly as you scale things up from, let's say, here is a small mammal, that if you go up to the scale of a large mammal, the proportions change, as you scale up. And there was another reference for me is going back to Myron Goldsmith, is an essay he did when he did his master's thesis under Mies van der Rohe, which is on issues of scale in tall buildings. And it has some very, very seminal ideas that he repeated in his monograph here from Rizzoli. And so, going back to Myron, when he did his thesis under Mies van der Rohe, he had, in his thesis, he talked about issues of scale. And here he has a series of drawings of bridges, depending on the span of the bridge. He has different solutions, and he has, what is the appropriate solution for that scale? Now, this thesis was done in 1953, and what you'll notice that there's a very common structural system that was not common then, that's not on the chart. You might notice that there's no cable stayed bridges in here, which has became dominant. It was actually, even though the idea had been around for a while, it was really became prominent after World War II, when the Allies managed to blow up all the bridges across the Rhine, and the Germans, some very brilliant German engineers, needed to span all these rivers with some very efficient structures. They came, that the cable stayed bridge came into prominence. And so when you think of this, when I look at these, I think of them not as solutions or systems, but actually perhaps as species, like animal species. And unlike nature, where one species evolves from another, we in design, architects and engineers, we can create a whole new beast or animal or species just by creativity and respecting physics. And certainly scale and form shows up. On the left is the scale of the bones of this house we did with Tom Pfeiffer. On the right, the scale of the bones of the Willis Tower, the Sears Tower. And so when you look at a chart like this that was started by Fazlur Khan, I think inspired by the work of Myron Goldsmith, we have these different species of potential solutions for tall buildings, depending on how many stories there are or how tall they are. And certainly over time, we've been able to evolve, but in the height of buildings. Here's a chart of the nominally, some of the tallest buildings in the world in their era. And you might notice that the Burj Khalifa is substantially taller than whatever came before it. And the reason that was possible is because we looked very seriously at the issues of scale. If we had taken like an existing solution and just made it, scale it up, it would not have worked. For instance, if I were twice as tall, I'd need to be twice as wide and twice as thick, and I would weigh 8 times as much, which is why scaling doesn't work. You can't just scale things up. You have to create something new. And this particular solution we have here doesn't have to scale by the cube, it only scales by the square. So therefore, if I were to make it twice as tall, I'd have twice as many levels. I would have, the wings would have to get longer, but it would not have to get necessarily any wider. And so, this type of a system is scalable by a different rule than say Galileo's bone or a building like the Sears Tower. As Silvio was so kind enough to point out, we've had this exhibition, it's moved around the world, where, as those of you in practice know, whenever you have a client meeting, you make a model that's, so big, maybe a foot tall, or maybe a foot and a half tall. And that model, it doesn't matter if it's a 10-story building or a 100-story building, the model's the same height. So what we decided to do is make a series of models of buildings that were all at exactly the same scale, 1 to 500, okay? And we also decided to just model only the structure. And the question is whether or not, is the structure and the architecture married to such a degree that without the skin on it, the architecture is still there. And I think you could argue that that's the case. Certainly on here's at the lower left is the Exchange House I showed you earlier, followed by Inland Steel, a project that we just finished in Utah. And so, and we made these models out of laser cut museum board where you modeled the entire external structure, all the interior columns and every floor, or at least every major floor. And so each of these models have all of the structure. And this is the Chestnut DeWitt Tower I mentioned earlier. This, of course, is the John Hancock or the Sears Tower. Clearly, the architecture is still there without the skin. This is a project I'll talk about in a moment that we did recently in Australia. Another one we just finished recently in China. Another one we finished a while ago in China. And of course, like all designers, some of my favorite designs of all times were the ones that didn't quite get built, such as the Lotte Super Tower, where it was a diagonally braced tube of a building that went from a square to a circle. Another very, very important topic is hierarchy and order. Once again, I'm not talking about not the hierarchy in the sense of who comes up with the ideas, but hierarchy in the sense of how do we tell the story. And so let's talk about the Hancock building in Chicago, the hierarchy and order. And clearly there's a clear expression going on here of the verticals, the diagonals, some horizontals, and certainly the corner columns. And when you look at the Hancock, it's important to remember what we call the rule of the Hancock, which means that every time a vertical crosses a diagonal, it happens at a floor line. So every time a vertical crosses a diagonal, it happens at a floor line. And because of that, you're able to move you're able to move vertical loads, at least the symmetrical component of vertical loads, anywhere you want. So you can put all the load in the corners, or you can bring the load from the corners to the individual columns, however you wish by proportioning the columns, and the load will go to that column. And so in many ways, the Hancock is a tied arch. In fact, it's a series of embedded tied arches by these trapezoids in the triangle. And so, so each of these horizontals are important. At least the horizontals in between the diagonals are very important for moving loads around. But there was a discussion about, you know, I was not part of the design, of course, it's before my time, but you know, what to express and what to not express. And here's a diagram from our archive talking about how you can put some loads at the top, and by the time you get to the bottom, they're equally distributed because of this technology. And here's a construction shot, not unlike the model I just showed you a minute ago. Now, sometimes we have a couple of phrases here in the office. One is like we call it the Dolly Parton quote. As I said earlier, to make something simple is not easy. And so the quote we use is it costs a lot of money to look this cheap. That's the Dolly Parton quote. Another quote that we have is, we used to say you have to lie to tell the truth, but now we say sometimes one must distort to make clear. And let me go back to the Hancock. Now, here's a construction photo of the Hancock. And it has one basement level, and you have the sunken plaza, okay? Or no, let me take that back. You have, this is essentially, the ground level. This is one level up. And structurally, the right thing to do is this diagonal should hit the column down here in the basement. It would look ridiculous because you would come up to the building and you'd have a diagonal disappearing into the pavement. What does that mean? And so instead of doing that, doing what's really the most, in order to tell the story of the building, tell the story of the structure, what was done was not the most pure structural solution, but a little distortion to make the story actually more clear. And so not only was the diagonal not only brought up out of the basement, it was put one story in the air. So when you come to Chicago and you walk down Michigan Avenue and you look at it, you will see that the resolution of the vertical, the diagonal, and the horizontal happens on a pedestal where you can see it completely resolved. This is a very important discussion that's going on behind you. And then even furthermore, to have honesty, if you look through the ground floor windows, you will see the diagonal that is carrying the windows to the basement. It's not hidden, but it's not expressed. It's not emphasized. And so, that's a very, very important distortion to make the story clear. Here's another project we did. This is a Clemson, School of Architecture, where we express this pyramidal, upside pyramidal structure that's centered on the skylights to express the hierarchy, or this church we did, this cathedral we did in Oakland, California, where you have the hierarchy and order of all the systems layered together, or the project we did in Detroit for General Motors, the systems, how they come together, their hierarchy and order. And let me talk a little bit about Exchange House in London, which, the reason it's a bridge is because it's covering over all of these tracks. Well, and it's in the switching area, so that none of the train tracks don't really line up in a kind of organized manner. And it's a tied arch, basically. Well, fundamentally, it's a tied arch. And so that is the most important aspect of this building, is the tie and the arch and the abutments. Here's the working drawing that we did on this, and when we thought quite a bit about trying to tell the story of the structure through the architecture. Here we had them pre-assemble the arch before it was shipped to be sure there were no tolerance errors in the field. The last thing you want to do is have that up in the air and have something not fit. So here they are pre-assembling the arch in the fab shop, and here it is being constructed. But let me talk about this particular connection, which took a long time to come up with it. And so everything you see here is essential, but not equally important. This column back here, it's essential, but it's not as important as the arch or the tie. And so the alpha, if you might say, was the alpha family was the arch, the tie, and the abutment, and they are clearly given prominence. And then the columns and the other members are essential but not equally important, and they're held more quietly. And this applies not only aesthetically but technically. A lot of times when you're as an engineer, when you design a connection, you got to decide who gets the right of way. I hate splicing tension with welds, because you increase your risk. So maybe the tension member gets to go through and the compression member is interrupted, because our compression load connection is much more reliable than a tension connection. Efficiency and economy, which is the heart of all of us. David Billington from Princeton always had the quote of efficiency, economy, and elegance. Well, let's hope elegance is always there. That's kind of the starting point. But efficiency and economy, particularly today, where we're worried about carbon, and the most important carbon is the carbon we spend today in the built environment, and that most of that embodied carbon on day one is structure. And so we've been doing a great deal of work in trying to come up with more efficient tools for more efficient design. But efficient design can lead to beautiful architecture. I mean, that was the basis of this work by Fazlur Khan and Myron Goldsmith in creating, something that minimizes the premium that's required for height. As you go higher and higher, how can you minimize the premium that has to be spent because you are taller? And I'm totally convinced that the most important parameter in the design of efficient architecture and engineering is geometry. Geometry is where architecture and engineering comes together, and it's a huge issue. And we talk about three components. We talk about topology. By that we mean, first of all, you have a design domain. Where can the structure exist? You have topology, which by that I mean what is connected to what. Then you have shape, and then which is how you take that topology and shape it. Then finally, you size, where you size the members and the connections. Here are two structural systems that do exactly the same job. For equal tensile and compressive stresses, the one on the left for strength needs 27% more material, and for deflection it needs 60% more material. That's ridiculous. Not 6%, not 16%, 60%. And the difference between these two trusses is geometry. And this knowledge needs to get out there. And so and what is the difference between these two? Architecture. And so, the topology of the structure and the shape of the structure needs to be part of the very initial discussions of the creation of the architectural solution. We've been looking for benchmarks through the work of Mitchell trusses, which from a very famous paper by Mitchell in 1904. And we've been creating geometry. We've been discovering each of these have an infinite number of members. This half a bicycle wheel has an infinite number of spokes. Well, that's hard to specify in our world. So we've been come up with discrete solutions, which are kind of unusual. The things we're not comfortable with, things we are not used to seeing, which are more efficient than what we're used to seeing. And how do we explore these? And we've been taking this into some of our newer buildings where we study this. For instance, here's a project where we took this research, and this is a concrete building that's braced by steel, which is a conversation all by itself. And you might notice that it's a high-waisted brace, not an X-brace, because it's more efficient, because nature likes to turn the loads gently. So the wind load comes in, it turns downward a little bit, it hits the building in the middle, turns down again, and finally hits the far side and turns vertical. And in this process of turning the load gently, you get a much stiffer structure, and that needs less material. Also, it's important, people like to do very, very slender buildings. At some point, it becomes very expensive that the amount of material you have to add to the entire building for that last floor is a very important thing to do, and you should be very cautious about when you build very, very slender towers. One of the things is, can you get rid of whole systems? Here's this house that we did with Tom Pfeiffer, where the columns, this is the column, it's actually a 60 millimeter square solid steel bar stock, but only 60 millimeter square, that holds up both the roof and the cladding. A lot of times in architecture, we're worried about liability and trades, and getting the trades to talk to each other. And so, normally you would have a column and a mullion, either one, which is, in fact, when I came up with this because I used to do most of my preliminary engineering by hand calcs. And I was sizing the mullion because they have like hurricane winds up in New York. And so, I sized the mullion and said, well, heck, this can hold up the roof. So I'm either going to get rid of the column or the mullion, or I'm going to have one element that does both. And I recently did this. This is up in Canada. We did it for a good Toronto a company called Manulife Insurance. Anyway, so this is the plus 15 level in Calgary. So in the wintertime, you can go between all the buildings. And here is another one where we had this combination of a tied arch and a funicular that share the load. And you'll notice that there is no mullion, that we actually glazed to the structure. We eliminated an entire system. Because before I did this bridge, I went up to Calgary and walked through all the plus 15 level bridges, and I noticed that usually the mullion was bigger than the structural element right beside it. So I found that a little unsettling. So I decided to try to simplify. And certainly timber, there's a lot of good timber being done in Canada. We're doing a lot of ourselves, particularly on the West Coast, but we also did a lot of just fundamental research in how to get timber into tall buildings. In fact, this research project on the left was based on the same program as that concrete building I showed you earlier, the Chestnut DeWitt building, that was done almost 50 years ago. And we're becoming convinced, as the right way to spend timber is in the floor systems, because that's where you get the best benefit for the limited timber we have today. Let me finish up with a little bit about the Burj Khalifa, and what we have on this. It's primarily a concrete building. It's a residential building. It's certainly pretty extreme. Were we facilitators of dreams or enablers of excess? We try to be the first and not the latter. It's a very kind of minimalist system. It's some walls, some slabs, and a few columns. If I do it again, I get rid of the columns, and simple things arranged in a different way, if you will. And so we came with a structural system, which after quite a bit of work, in fact, a lot of this was determined through working with interior designers on how it laid out, because we actually started with a different initial assumptions system, and then it evolved into this. And so basically what we called it a buttress core. Here's this hexagonal core in the middle. The core does a very important thing. It keeps the building from twisting. It's like an axle. The most perfect axle is a circle. And so a hexagon is pretty close. And so it's a very, very stiff that won't twist, but it's much too slender to go to great heights. So we ended up buttressing it with the three wings, where we had web walls, if you will, going down the corridors. And then we had demising walls between the units which we use like flanges, like you would have flange on an I-beam. And so, as I said at the beginning, my firm is called Skidmore and Zamerl, but the initials are SOM, which in reality means stay on module. Okay, so SOM is all about the module. And so here, this was a 9-meter module. At first we had an 8-meter module, but eventually it morphed, mainly driven by interiors, into a 9-meter module. And so when the wind pushes against two of the wings, it's resisted by the third wing, just like this man is. So this man is kind of the essence of the structural system of the Burj Khalifa. You have wind against his umbrella. He's resisting it. His front leg is like the core, and his back leg is like the buttress. And he's using his weight to resist the wind. And we did that on the Burj Khalifa. This is a section through one of the wings. So this is the middle of the building. This is the extreme. And we forced the gravity loads outward. Gravity is amazingly reliable. You can always count on it. And so we managed the gravity. And so, and because of that, this is the reinforcement of the world's tallest building at the ground level. If you'd walked up to that, you would say, and someone asked you how tall that building is, what would you say? 5 stories, 10 stories? Not 160 stories plus. But even in a windstorm that happens once every 1,700 years, we have no uplift in the building because we were able to use the weight of the building effectively. And as everyone knows, the most expensive thing in reinforced concrete is not the concrete. It's usually either the formwork or the rebar, often the rebar. And because of this, we were able to minimize the rebar. Wind is the dominant thing in tall buildings. And as wind goes past an object, you get this buffeting from side to side. And every time that does, it puts a pulse lateral to the building. If a tall building were ever to fall over in the wind, it would probably fall over sideways, not in the direction of the wind, because of this pulsing, which is like a child on a swing. And because of the geometry of buildings, the range of expected geometries in buildings, and the wind speeds that you're likely to get in this world, it's highly likely that you're going to have a windstorm that's going to be where it's going to be pulsing vortices at the natural harmonics of your building, and you get a resonance effect, a harmonic resonance. And so we did a great deal of wind tunnel testing, and we reshaped the building many times. We did what's called force. We of course did all this in Canada, very close to Toronto and Guelph, at RWDI's wind tunnel library, which they have a nicer facility these days. This used to be in a strip mall in Guelph next to a Chinese restaurant. Anyway, so we did some very sophisticated aerial elastic models where we could pick up the higher mode shapes. It's very important. Well, we did some very special testing on parts of the building. This is down in Ottawa. This is the 9-meter, the 30-foot tall wind tunnel. There's Peter Irwin and some of the RWDI staff during this test. We then, on the structural side, tune these things like a musical instrument, particularly the mode shapes, and so to where we want. And in this process, we discovered, the building has 6 principal directions. The wind going into the nose, where it acts like a cutwater, and the vortex that would form would be downwind of the building and not particularly important. But when the wind hit 2 of the wings, the vortex would form and push against the 3rd wing, and that was an issue. So what we had to do is went through a lot of reshaping of the building through the design. Instead of that child having 2 feet that kick in harmony with now this child has, this building has maybe around 27 feet, and they all kick at different rates. So you get much less forces. In fact, on the left is our very first wind tunnel test. By the way, the building did not work on the first wind tunnel test. And after we reshaped it a few times, the forces had dramatically dropped. And so here's some of the testing we did, including one that was taller than we actually built. And what happened is our initial scheme, which did not work, we were able to grow the building by 310 meters, which is the size of the Eiffel Tower. That's a change in height. And our forces went down, and our movements went down. And one of the other parts of my philosophy is that's kind of related to this problem is I always hark back to the Hitchhiker's Guide to the Galaxy. And in that book by Adams, you might remember that what does it say on the guide? The famous Hitchhiker's Guide itself. in bright bold letters, it says, "Don't panic." And that's it's one of my philosophies. When things go bad, and they will go bad, don't panic. It will not help. You just need to like calm down, take some deep breaths, and address the problem. And the fact that the initial scheme did not work is probably the reason we were able to go so high, because we had to, if it had just worked, we might have just stopped, because this was the world's tallest building. It was 518 meters tall. It was 10 meters taller than Taipei 101. So check the box, world's tallest. But because it did not work and we had to do some radical changes, we were able to go much higher. Of course, the construction technology was phenomenal. They figured out how to pump concrete 600 meters, and it still came out as concrete. The construction was quite remarkable. The foundations went in early, and then it sat there while the owner was negotiating with the contractors. Then in April 2005, the main contractor showed up, Samsung, and went up, and essentially a vertical factory went up and up. And let's talk about the Burj effect. Every day, thousands of people go to Burj. This area was essentially an abandoned military base. It was 1 square kilometer. And nowadays, you have this building with all this, development around it. And every day of the year, thousands of people come there to see the lights, to hear the music, to experience it. And so as it is today, one cannot imagine Dubai without it, or UAE, or the Middle East, or I hope you would agree, the world without it. That this incredible effect that this project has had on Dubai, and I think the world. And so with that, thank you, and I open it up to questions. I invite Silvio to come back.
No, thank you for that. It's that was a fantastic presentation, and it's not only I didn't know what to expect, but not only was it about engineering, but it was about architecture, and the design philosophy just flowed from one to the other, as I would have expected a firm that is about architecture and engineering. And just to pick up on the Burj effect, we had a very small part of it, being involved in the architectural contract administration portion. And
I should have said, the NORR office at the site was right next to the SOM office. Because SOM was not licensed in Dubai at the time, so NORR was our collaborators and the architect of record for the project.
Yeah, and Hans Kraus, who worked on that, still talks about it to this day. So that Burj effect really had an effect in our office. Right. But thank you for that. I'm going to bring on 4 panelists to ask the first question. So if the panelists can please turn on their cameras, and I will introduce them one at a time. So I'm going to start off with Professor Sigrid Andresken. Her research interests are in the mechanics of large-span structural surfaces under extreme loading, and more recently, under resource-constraint construction conditions. In 2021, she was named Fellow of the Structural Engineering Institute of American Society of Civil Engineers, elected Vice President of the International Association of Shell and Spatial Structures, and received the Digital Futures Meritus Ripperman Award, and at the University of Missouri, and she received the ASCE George Winter Award. She chairs the IASS Concrete Shell Roof Working Group. She is the co-editor of International Journal of Space Structures and directs the Forum finding lab at Princeton University, where she teaches courses on nonlinear mechanics of solids and slender structures, structural design, and the integration of engineering and the arts. Welcome. The next panelist is Yahya Yan, who is based in Dubai. Yahya is the president and design director at NORR with 4 years of global experience. Yahya leads NORR's design efforts in the Middle East and Asia. Yahya undertook his undergraduate and graduate studies at Princeton University, is licensed architect in New York. Yahya lived and worked for 14 years in the US before moving to Dubai in 1996. Yahya advocates integrated design in a means to transform our built environment. He sees design as a patient search, equal parts analytical and intuitive. The next panelist is Professor Edmund Salikas in the Department of Architectural Engineering at Cal Poly, where he teaches structural engineering courses as well as architecture studies. He earned his PhD at the University of Wisconsin-Madison and is a licensed civil engineer in California. He is the author of 3 recent textbooks: Architectural Structures, Visualization of Road Geometry in 2022, and Structures and Studio Approach in 2020, and Structures and Geometric Approach in 2018. He recently co-authored a chapter entitled Thin Shell Concrete Structures for the latest edition of Structural Engineering Handbook. And our 4th panelist is Hassan Safarini, who is principal of NORR and has headed the structural engineering group for more than 12 years. He is also the design engineer for NORR's largest adaptive reuse heritage project, which is Toronto Union Station redevelopment with a dig down expansion never attempted at this scale in Canada. He obtained his PhD from UC Berkeley and is a full professor of civil engineering and now an adjunct professor at Metropolitan University in Toronto and has published many international research papers. So welcome to all 4 of you. And I'm going to start with Professor Andreasen to ask first questions to Bill Baker on his presentation.
All right. Thank you so much, Silvio, and thank you, Bill, for inviting me to be on this panel. Bill, thank you so much for your presentation. It's been really amazing. Mostly when engineers present, they either present about their projects or they present some complicated methods. And you've given us an opportunity to really almost look into your soul, as in how you do the stuff you do, which I have, that it's really a privilege. To hear you talk about things that maybe are not so easily expressible, or definitely things that we don't really learn in engineering school, as to say. So I want to talk a little bit about that. You say, that you as a designer need to have a position, right? You need to have a design philosophy. And you mentioned that, amongst other things, you started thinking about that when you were working with James Turrell, the artist. You also mentioned religion, but I wonder whether you can, and this is also more for the younger people that are maybe, I don't know how old they are, but maybe 18, 20. How do you start developing a position? How do you start developing a design philosophy? What should you be doing? Or in your case, who was influential? Like how does this happen, right? Because it might or it might not happen at school. So.
Yeah, and I actually didn't start doing a deep dive until I was more mid-career, and it really was. I don't know why those 4 words, no, Quaker simplicity, why those 4 words affected me so. But I thought, well, what does that mean, And then as I examined, like I said, I knew nothing about Quaker religion. So as I examined it from the outside, I made some observation, and I connect what I saw there what I could understand of the religion to what James was creating in art. And it made me think about what is the connection between your ethical values, because all those things are not necessarily aesthetic, simplicity in speech, stress, the phrase "step into the light" is not an artistic statement. It's about something else. It's a religious statement. But you take that, and then I started looking. If you go to Germany, and you look at a Lutheran church versus a Catholic church, you're in the middle of Germany, or better yet, a Lutheran church that used to be a Catholic church. And how the aesthetics changed to that, and so it made me start to think about it. A lot of this stuff was already kind of there in the sense, we're as engineers, we're trained to do things as precisely, and try to be economical. I did happen to grow up in an office full of people from East Van der Rohe's office. And so I was, which is all about minimalism and stuff like that, and structural expression. And I happened to be luckily in an office that where structural clarity was kind of central to the architecture, because that's just, who we are. And so all those things, so it was kind of like all this stuff embedded there. And then I asked myself the question after everything had already been planted. Okay.
Yeah.
But part of it, we're in because of the climate crisis, people maybe need to ask that question earlier in their career, like right now. And I can tell you, it's very, very satisfying to design a very complicated structure for a problem that did not need to exist. Okay, because you're solving a really hard problem, and you come up with a solution. You think you're very clever, and it's probably maybe wasteful. And we've all done it. Okay, on the design side, we go back and say, oh, maybe I shouldn't have done that building. And before, if you go back a few years, before we really understood, this climate crisis, if somebody was particularly wasteful in a project, you'd say, well, it's between them and the owner. If the owner wants to write a really big check to construct something that's much more expensive than it need be, their business. But when you put it into the climate thing, it's actually everybody's business. And so I think it's, this conversation needs to move forward, but it's clearly not part of the education of engineers to have developing a philosophy.
Yeah, and to have social responsibility. So also what I understand from you going to work at a young age at the SOM, you kind of by symbiosis kind of maybe absorbed all this, and it was only maybe later that you were able to articulate what was exactly so important when somebody prompted you, right?
Yeah, because like I say, I was just lucky. Fazler Khan went to U of I, Hollanger went to U of I. There was kind of like a little pipeline from Champaign to Chicago. And a professor put me in one end, and I popped out over here.
Right.
And so I don't underestimate the value of luck. Okay.
Yeah, luck as in being at the right time, right place. Yeah.
Though I do urge the young people on the call, your first job is really, really important because you're still malleable, and don't go for who's going to pay you the most money. Go for where you're going to learn the most, where you get the best preparation for your career. And I got lucky, don't. Your first job is very important because you'll develop a philosophy that will stay with you, or some inherent values that will stay with you for your entire career.
Yeah, I have maybe one more question. I'm going to tell you a very bad joke. The joke is, it's not my joke, right? If architects build all the buildings, they would fall down by their own. If engineers build all the buildings, they'd be so ugly we tear them down. So obviously this does not relate to the work of SOM, right? To be clear. But so my question really relates, because you have mentioned architects and you've mentioned interior designers. So what is the secret to working successfully together? Who's the boss? Maybe there is no boss, or how does this work successfully? Because obviously SOM is a very integrated office. All the works that you've shown is, structures, architectural form maker, structures integrated in architecture. How do you do that?
Well, firms like NORR or SOM, where you have architects and engineers working together, they're somewhat self-selecting, okay? So the people who come to work at a firm like ours, if you're an architect, you come here because you like to work with engineers, or if you come here as an engineer, you like working with architects. That helps a lot. There's a lot of mutual respect. The architect is the orchestra leader, but if the first violin says we're not going to do it, guess what? We're not going to do it. Okay. So it's a lot of mutual respect, and architecture is a lot more complicated than doing like bridges. Okay. Because there's so many things in play, that you have. It's a series of compromises. In the end, somebody's got to make the call, and that's usually the architect. But I have to say, the architects I've been lucky enough to work with respect their team. And if somebody's, says, this is not the way we ought to go, then collectively we find some other way. The other thing is, don't underestimate the creativity of your colleagues. Sometimes you can solve a problem, but maybe you shouldn't. Let them try to solve it. Okay. And see what they come up with. You can always play that card later. But so there's a lot of finesse in it. Okay, there's a lot of finesse, but it starts with mutual respect.
All right, thank you.
Thank you for Professor Andreasen. I like your joke, but I always like to say in our office, it's always nice to work with engineers that think they're architects, and architects that think they're engineers. So we'll move on to an architect now, Yaya Yan.
Thanks, Silvio. Bill, first of all, it's such an honor to hear you speak again. And certainly in the Middle East, you have many admirers for your work. And looking at your presentation, I believe we're all reminded that great design actually makes no distinction between architecture and engineering. And it makes no distinction between art and science. So in a sense, my question is that in an age of super specialization, we live in an age where complexity seems to have drowned out simplicity. And all the disciplines in the world that you look at seem to be so super focused and so super specialized. I think we face a tremendous challenge. How do we break down those boundaries and find truly integrated, multidisciplinary solutions? Certainly, we struggle with that. And I'd love to hear, as you look back on your own career, if you have any thoughts on that challenge.
Yeah, that's a very, very, very important point. And it's not to the, people are drilling so deep, narrow and deep, and they're not seeing the big picture, and that is a problem. And it shows up in various ways. I happen to be on I don't know how this happened, but I'm on a committee in London, the UK, on construction productivity. And one of the problems we have in London, in the London market, not SOM in particular, is that you'll have a design firm who's able to get planning permission, and then you'll have another firm that does the working drawings, and then maybe somebody else does the construction administration, and there's no feedback loop, where God bless you if you get to take a job all the way through and you get to the field and say, well, that didn't look very good, and you learn from it and you go back. But that feedback loop is missing from a lot of what we did. One of the things that is a lot of those people I showed earlier that invented new things like Candela and Friado, very, very limited computational power. You know, that maybe intuition, maybe a few equations, a lot of models by people, you know, experimenting. And I make models all the time. Just when I have an idea, I make a physical model. It helps me understand. And so I don't think we've quite figured out how to harness the computational power we have now in a way, the way that's beneficial. You know, a few years ago, I think it's actually better than it was. A few years ago, when we first started getting these incredible Rhino programs and stuff like that, you know, people were building, you know, were drawing eye candy, and some engineer was figuring out how to make it not fall over. Okay, you know, it was not elegant, it wasn't integrated. It was, you know, somebody makes some eye candy, and an engineer figures out how to fit some structure into it. I think we're moving beyond that, and quite frankly, the climate crisis is helping us focus on that. But actually, I think it's part of it's going to be part of self-discipline, and one of the things that I do almost all of my preliminary designs by hand in a sketchbook. Okay. And the reason I do that is that it makes, because I can't calculate complicated things, so it makes me make the problem simple, okay? And then I come up with preliminary ideas and sizing, and, you know, I don't need a million numbers, I need maybe 3 or 4. How much does it move? What are my quantities? Do I have uplift? You know, I don't need that much. And so it helps me keep it simple. And then when we go to the computer, I see things that are, if I see something that confirms what I did, fine. If I see something different, then I learned something, which wouldn't happen if I turned on the computer initially. A couple of years ago, we had a competition for a computational project I can't speak about. It was very, very challenging problem. And so I got about 6 of my best engineers together. And for 6 weeks, no one could touch a finite element program. For the first 6 weeks, everyone had to do hand calculations, or at most an Excel spreadsheet to keep their arithmetic clean, okay? So we actually had to think for 6 weeks, okay? And by the time the 6 weeks are over, we own that thing. We own that design. We understood all the things. And then we put in the computer and then focused on the box, you know? We stopped thinking about the problem and started thinking about how to run the computer. But going to one of your fundamental questions is, where's the master architect, the master builder, who's going to be able to know the values if they're educated within narrow things, and somehow there has to be a path forward for the generalist, or the person who does see the big picture and doesn't get lost, you know, and the talent doesn't get lost down some narrow alley, you know, but somehow it comes back. And as you guys, you know at NORR, you know, I mean, we sometimes meet hourly with the architects and the other engineers, the MEP and the electrical and the plumbing, you know, and by the time you do that enough projects, the architects are trying to solve the electrical problems, you know, we all know that the conduit turning radius for a high voltage line, you know, as we try to, and so yeah, we are in a time where it is getting away from us, and the leaders in the industry need to figure out how to not go too far down the path we're on now.
Yeah. You know, you said a few words there which really resonated. I mean, I think in some ways we are in a time in civilization where we think less, but we do more. And obviously you believe in thinking, you believe in the sketches and when I was growing up and I was studying structural engineering in my early career, we used to pull out a slide rule to do a quick test on whether the modeling, yeah, exactly, the slide rule, there you go, yeah. And that's a great way to know whether you're off by an order of magnitude, because sometimes you can be off by an order of magnitude, right? And one of my concerns, looking at the younger generation, and they come with tremendous talent, the younger generation of designers, whether they are architects or engineers, they're very talented. But I do have one reservation, which is the over-dependence on somebody else to solve the problem rather than using your own intuition and gray matter to chart. I call it charting the path through the forest. Somebody has to chart it,
Right.
and then you work at it, right, until it works. And that's the risk, I think, in our education system, perhaps in our universities, in our practice. I don't know if you share that, or am I being overly simplistic in that?
No, I think there's a, this fundamental understanding. I've worked with a lot of architects who have a deep understanding of structures. Could they do a moment distribution? Never. Okay. Could they calculate the flexion of beam? No. But boy, do they understand structures. Because they have a deep understanding, because they embrace it. They want to understand it, and same thing. The best engineers out there are the ones who try to understand architecture and the other disciplines. The MEP is essential to our buildings. We need to understand that, in sustainability, and the like, and vertical transportation. We need to understand as much as we can about the whole problem, and without, because you can get one of the things I speak about a lot is the why is much more important than the what. These experts can give you what the answer is, but you need to understand why is that the answer. Because once you understand the why, perhaps you change the problem. And I think in a not too distant future, we're going to be okay. Let me go back. If you go back, I don't know, half a century, we had very limited computational power. Okay, and so there are a few equations, so you had to do things that were to be calculated. Well, when I was a young engineer, most of our buildings were doubly symmetric because you could not fit more than a quarter of the building in the computer. Okay, so you had all this discipline came from the computational thing. Now I would say we're in the computational age, where everybody knows how to do Grasshopper and Python and all this kind of stuff. I think in the not too distant future, we're going to be in the post-computational age, where the young people, guess what? You're not going to be pushing the buttons anymore. AI or something that's going to do that. And what is your role? Your role is understanding the why. As these programs give you the what, here's the solution. You, because of your deep knowledge, will know why that's coming, why that's giving you the answer. And once you know the why, you know how you can maybe perhaps change something to end up with a better design because you changed the problem.
That's interesting.
Yeah.
I just have one quick one, Silvio. I may be hogging more time than I should, but you talked about the environmental crisis, and certainly there's a growing awareness finally that we've messed up. Over the last 200 years, the Industrial Revolution, we really messed up, and we need to clean up our act. And I'm wondering whether we need to go back and look at nature, and you talked about that a bit. Maybe we should be more serious in how we study how nature adapts and how plants have phototropic abilities, and how the roots of a tree actually reach into the soil and find nutrients, and how do those make their way up the trunk. I mean, maybe we should really have an intensive, dedicated research into that. And who knows how that will affect structure and architecture and MEP and vertical transportation and the facades on buildings. I don't think we're doing enough. And I wonder if what your thoughts are on that.
You know, I think it's important. I take kind of the Darcy Thompson approach, which what are the you know, because nature reacts to its environment and physics, and I think you get inspiration from nature, but also from studying what is the problem that nature was resisting, and its solution. Then you know, how do we look at, you know, for a topo engineer, I live in a single family house, and we have trees on the south side of the house. In the summertime, they give us shade. Right now, all the leaves are falling off, and in the winter, we will be warmed by the sun. You know, so through the winter, it's like, wow, how cool is that? You know, but no, I do think going back to you know, to what is, you know, the fundamental problem, you know, of the environment, you know, energy and everything else, and the forces of nature, and looking at it from the basis, and then, you know, what is the solution we do? And also, if we see a biological solution, don't just apply it, but understand why is that the solution, whether or not that why applies to your problem. Sometimes I see people just kind of superficially apply it, and that's probably not the right thing to do.
Yeah, absolutely. Thanks a lot.
Thank you, Yaya. So we'll move on to Professor Salifas.
Great, thank you. And Bill, you know, I've heard you speak many times, and this was really, really good. I know you're a friend of Cal Poly. Please come back and visit us again. As everybody else on the panel, please come visit us here.
Will you take us to the barbecue place?
Yeah, and the fish tacos. Yeah. So I'm going to ask you some hard questions since this is your oral exam here. Okay. So not these broad questions, but I'm going to dig deep. I want to talk about Farnsworth House and that Miesian detail of the column hitting the side of the beam. You know, that's a signature piece of the architecture, right? And many people have written about it. Herzog and Demure wrote a book about it. But is it structurally clear, or is it a bit of excess? You know, is there, you know, that idea of what is going on there? Was it worth it? You know, and that, was there some hubris of the architect there? Can you comment on that, just on that detail?
I actually happen to have the calculations for the Farnsworth House on my laptop here.
Yeah, so do I.
Yeah, because Myron Goldsmith did the calculations, the moment distributions, and it actually works reasonably well. You know, we recently, they found some drawings of an unrealized Mies building from the 1950s. It was you know about this, it was a fraternity house for University of Indiana. And at some event at the university, some donor said, you know, by the way, I have all these drawings that Mies did. And so we recently executed, we were recently with the engineers of record on a Mies building in the year 2021, 2020. I was the engineer of record, okay, for Mies, you know, and so we went through and guess what? All those beams were like right on the money, okay. You know, and it took us a while to figure out the moment connectors. And for those who don't understand, the beam flies by the back side of the column, and it's welded with some plug welds on the back side, okay. That's able to develop the moment connection. And so it's off to the side, and so I don't think that's too bad. One of the interesting things about the Farnsworth House is that, you know, you have, you know, there's only two levels, the floor and the roof, okay? The floor has much heavier loads than the roof. So rather than have a big beam on the floor and a little beam at the roof, they made the floor beam undersized, and they made the roof beam oversized, and they used a steel mullion to connect it. So they deflect together. So they share the load. So half the load goes to the roof and half the load goes to the floor, even though it's not equally distributed at the distribution. You take the big load on the floor and the little load on the roof, you add them up, divided by 2, guess what? That's what's in each beam. And so you had this uniform size, but it's actually a pretty efficient idea. You know, to deal with this. So I think that was very, very clever.
It was.
So now as you may know, I did an upside down Mies house for an artist. It was Inigo Mignano Vea. It was at the Mass MoCA Art Museum in Massachusetts. And so Mies did a series of 50-foot by 50-foot houses. And so what Inigo did, he did like a 25-foot by 25-foot house, but then turned it upside down. And so I was the engineer on that. And instead of putting the columns in the corner, we put the columns in the middle of each of the faces, like as Mies did on one of his projects, one of his solutions. And so I came up with a detail which was not the same. In fact, Inigo and I did it together. Because initially my solutions were I was just going to like rip off the connection detail from the Farnsworth house, but Inigo, no, he wanted to go a new way. So we developed I can't even exactly remember what we did actually, but we ended up with a different deal. I remember Mies's detail. I can't remember mine.
That, you know, for the students and the panelists in the room, you could find the talk at Northwestern University that Bill and Inigo did on that project. It's really, really fascinating. And then here's one more easy question for you. I know you know the answer, and you're almost past this oral exam here. Broadgate Exchange House.
Yes.
Is that a funicular or is that not a funicular, that arch on the facade?
Yeah, it's a I call it concordant. There is, okay, so it matches the moment diagram, and it is not curved. It's a series of straight segments, and that's a very, very important thing. You know, we had a bunch of debate about that during the design process, because everyone's used to seeing masonry arches which are constantly curved, but the thrust goes in a straight line from node to node. So to actually curve the member would be like building a crooked column on purpose.
Mm-hmm.
And at that time, David Billington from Princeton was doing the lecture circuit, and he talked about Maillard and Christian Men, and like Maillard occasionally, the famous bridge engineer, Swiss bridge engineer, and Christian Men, another Swiss bridge engineer, how Maillard occasionally would curve a line when he really should use a straight segment. And that he kind of was self-critical, and Christian Men went for the straight segments, and so you know that's part of it. I actually have this little 3D printed. This is a topology optimization study that we did for a bridge, and so you can see this is just an experiment we did. There's a couple things that I get more questions than I do get answers. You know, I get more questions than I get answered. This one is like, why is the tree only have branches at the top? Okay, and you know, and the like. But if you look at it, it's actually a straight line funicular.
Mm-hmm. Mm-hmm.
It's not a constant curve.
Mm-hmm.
That nature wants to go straight segments. Now, when we finished the building in 1990. You know, the Financial Times of London gives out an award for the best building of the year. Okay, we got number 2, and they said because we didn't curve the arch. Okay, now, okay, go fast forward 25 years. The American Institute of Architecture gives an award to one building in the whole world each year. It's called the 25-year award. So it's for a building that is you know, withstand the test of time. And guess what? Exchange House got the award the first year it was eligible.
Wow.
Only building in the whole world. So I feel vindicated. Okay.
That's great. That's a great story. That's really, really good. And I have a lot more questions, but I'll ask you at another time. Super.
Thank you.
Really fun. Thank you so much.
Thank you for those great questions. And we'll move on to Hassan Safarini.
Yeah, fantastic presentation. I think that all the engineering and the architecture educators on the call should take advantage of the fact that this is going to be on YouTube and direct their students to listen in. I think talking about structures at university in a system way, in how they behave is generally quite underdone, and then there is an advantage for both architects and engineering students to take advantage of that. So I think that is great that we have this now. I have kind of, I'll call it one question, but I'll think of it as one directed to the engineers and one to the architects. And in fact, I have actually quoted you a number of times from the time when we worked on the Infinity Tower, and the quotation is with regards to how intuition versus simulation and analysis are not always in line, and you astutely pointed out at the time how in selecting the best system for the columns, you had the choice of either stepping the columns or sloping them, and you had indicated that intuitively you had thought that sloping them would be a more efficient way of running the forces. And as it turned out, the computer model showed otherwise. And so very often people think that modeling actually moves the engineer from building the engineering sense, and in reality it does the opposite if you do it right. So that's my first point that I'd like you to perhaps elaborate on and comment on.
Anyway, I think it's always good to kind of like guess the answer before you see the answer, because if you get what you expected, then you're vindicated. If you get something different, you learn something. And I do believe intuition is an educated process. You're not born with intuition. I think it's created through experience, and you get a lot more experience if you kind of think what the answer is going to be before you get the answer. And that's one of the reasons I said earlier, like I like to do the hand calculations, because then I think based on my assumptions or the way I understand the world works, this is what's going to happen. Then sometimes it doesn't. Sometimes you get a little different behavior, and then also that's an aha moment. And now your intuition is more rich than it was. And essentially, we're talking about this Infinity Tower that we worked on in Dubai, and what it is, the building from the top to bottom, it was kind of an experiment in wind and other things. Where the top floor is 90 degrees rotated from the top floor, and the way we did it, and one would imagine, like if you take, like a lot of times if you take a structure and you just make the members finer and finer, you get the same answer. And so we were doing kind of like a barber pole where the columns were like corkscrewing around the building, and we did a very simple model, and we did that, and then we did another where we just offset the columns vertically. We'll lean them in and out in one direction, but in the face they just stepped over. And guess what? It moved a lot less. Because when you have a leaning column, you turn on gravity, it leans even more. And so we found that by stepping it over, it was much better. And our interpretation, which may be wrong also, is it's like a column on a pile cap. Okay, so if I have a column on a pile cap, the pile cap will deliver the load to the two piles. It'll split. It doesn't lean sideways. It just puts more reaction in one than the other. And so we had a spandrel beam, and the columns would, the step would happen on top of a spandrel beam, and the spandrel beam it's a small step, but that was enough to, yeah, it made a big difference, and so it was that was a learning moment.
Yeah, no, I use that. I've talked about it a number of times, and it's really quite telling. because even the most experienced and intuitively apt people can not necessarily get to the answer without the aid of the powerful model.
And I actually make a lot of physical models for structural behavior. I'm doing a lot of work with the artist Janet Eklund right now, as Sigrid knows, and so I to see how some of these things behave, I'll make a really simple. These are cable nets and things like so. I'll make a little model over here in I have a playroom next door, and I'll poke at it and say, okay, and then I do the mathematics. Yeah. So my second call it part of the question is, when you're thinking as a structural engineer and so on, and you're contributing to the actual form of the building, you're not just doing the math of the building, you actually forming the building. How much of an advantage would you say you had by being in a multidisciplinary firm, and would it have been the same if you were working with architects that are external to the organization? It's a heck of a lot easier internally, I tell you that, because you see each other hourly. Like the lead architect and I, we're just next door to each other, Adrian Smith, and then even some of the senior architects here, there's this one guy who's now a principal of the firm. I used to go to his desk and I'd have him stand up and I'd have him walk with me from his desk to my office, and we count the steps. And I say, it's only 25 steps away or 50 steps away. Come see me. So it was a lot easier. And I've seen on some of the more challenging projects I've seen out there in the world that have been where you really need to have really seriously good structural engineering. And I've seen it done a few times with really good architects and really good engineers coming up with a bad answer. Because the engineers just took the architect's drew and made it not fall over. Okay. And excellent engineers, excellent architects, world class, but the process was the problem. Right. Where you didn't get that. And what we try to do here doesn't always happen. We try to get everybody start day one blank paper. Now there may be some junior, some project comes in the office, so some junior architect will do a little code review, a zoning review, and you'll have, so here's the site, here's the mass transit nearby, zoning allows a building this big, the client wants a hotel. You do it, so there's basics, and everybody sees it the same day in the same conference room, except for the junior architect. And so you throw out ideas. I usually comment on landscape, okay, but everybody throws out ideas, and you can comment on architecture. Architects can suggest structural ideas, and so you end up with, like, you come out of the meeting with maybe 5 schemes or 7 schemes. And you go away and you test them, and then next time you end up with 3 where you merge a couple of the ideas or throw a couple away. And the other thing is the ideas don't go away. If it didn't work in that project, if it's a good idea, it'll find a home in another project later.
Right.
Because the team keeps going.
Excellent perspective. Yes, absolutely.
Thank you, Hassan. I think we're going to maybe move on. So going to move on to Ali Hussein, and I think we only have time for maybe 2 questions from the audience. So pick the 2 best questions that you have from the audience, please.
All righty. So there's lots of appreciation messages. Great presentation. Thank you. The first question from Carlos Gonzalez, who's an architect in our North Toronto office. He's asking, in the early 2000s, Peter Testa, an architect at MIT, and Marcus Schultz at Arab proposed a 40-story carbon fiber building. In essence, one of the first contemplated printed tall buildings. From your perspective, have these structural solutions evolved to where we'll see their implementation within our lifetime?
Okay. Yeah, the whole printed thing. We're all pushing on it, but I'm not sure we're gonna get there for the whole building, just because of the thing. I think there's been a lot of 3D printed components and stuff like that, or site manufactured. I'm on an advisory group at the University of Stuttgart, which Sigrid knows about, where they got like a huge bucket of money from the German government to come up with next generation construction technology. And there's going to be some where you might end up building your factories at the site rather than away, and maybe you're doing carbon printing. I think I haven't, other than small buildings, I haven't seen it yet, but I do think the philosophy of a vertical factory, and we're kind of halfway there now in concrete buildings, are mostly the way there. Because the form is self-jacking, which isn't that kind of like printing? Okay, you happen to have some formwork. The slabs, of course, you have to form. And one of the advantages of but the formwork is such that you can carry up from one floor to the next, and the only thing you have to pick up with a hook is the rebar cage, because you can pump the concrete. But the tall printed buildings, I haven't seen anything that's convinced me yet that we're going to get there, but I think we should keep looking.
Thank you. Another question from Eric. He is, so the question is, I particularly enjoyed seeing the foundation and or basement examples and how they're related to the overall building. In a way, they serve as a succinct full stop to the story written by the building's language. Interestingly, though, the public exhibit and book examples seem to have not shown these full stops. Is it because there is a lot of overlap across the structural species shown, and or they were indeed there but not perceivable?
An interesting thing is, if you look at nature, you have creatures that are exoskeleton and creatures that are in the bones are inside. Everyone on this call has a very substantial structure, happens to be on the inside. And if you see some poor soul who has cancer and their face is just, they've lost part of their jaw or something, and their structure is there. And so the expression of the structure doesn't have to be just purely exoskeletal. It can be internal. I think that's valid also. And so, a lot of times the just like in humans or most animals, the very important structure is part of the overall shape, as opposed doesn't have to be explicitly exposed. Like, of course, those are the ones that are really fun, like Exchange House, or that building in Australia I showed you with exposed bracing, or one of the things I love about pedestrian bridges, like the thing we did in Calgary, is you get to show it all off and the like. And so so sometimes you can really put it out there and on the outside, but sometimes it's not appropriate. And so I don't think you should corrupt the utilitas part of the design, the utility part of the design. And so we all have egos, but you got to be sure that your ego doesn't kind of get in the way of doing what's right.
Absolutely.
Okay.
Thank you.
Thank you, Ali. So just before I wrap this up, I want to take this opportunity to really thank the panel. Professor Andresen, thank you very much for being on, and hopefully we'll be able to see you in the future. Yahya, thank you for staying up till 10 o'clock at night from Dubai, and hope to see you soon. Professor Sadikas, thank you for the oral exam. It was a success. And again, hopefully we'll be able to see you soon as well. And Hassan, thank you for being on the panel. And last but not least, Bill, this was an incredible presentation. I think that certainly the NORR staff, our guests that were on the line, and all of the students, I think, enjoyed it, not because it was just engineering, but because it was architecture and engineering. And I can't avoid to do this, but I have to read this quote, which I think really wraps up the, what your presentation today, and it's your quote from 2010. And there's not too many people that I know. In fact, I don't know anyone that has the gold medal. I mean, we did a NORAD on Pierluigi Nervi, who is one of my favorites, obviously, and he's on that wooden plaque along with you. And the quote that that you put through in 2010, and I'll read it in its entirety. It says, essentially, a clear idea results in an informed aesthetic. It can yield a structure that is simple, elegant, and quite possibly easy to construct. I would urge all engineers to challenge themselves to distill their ideas into as simple and ideal as possible. So, when you look at the presentation that you did today, it's not just about, as I said, about engineering, but it's about architecture. And I hope that certainly that all of the participants, and I think that the number was somewhere around 250 today, will have heard you and will take that. And this was about teaching and learning and in improving their design capabilities. And I hope that everybody that sees this on NORAD YouTube learns from it. So Bill, many, many thanks for agreeing to do this and passing on your insights.
Well, thank you for asking me. I appreciate it. And congratulations for you to doing this series. It's really good of you to do this.
Thank you. All the very best.